Okay. Here it is. Okay. So here's it after they've already made that substitution. But from the image, you know that Polar is just going to love this thing because all the cross sections are circles. This looks like a parabola that's been rotated. And look at the equation. Doesn't it look like just a parabola equation? With a max of 9 minus r squared, it's the symmetry that captures a lot better than rectangular could ever hope to do. Okay, maybe. So how in the world do I set up this integral then if I wanted to find out here I am already forgetting my r. Okay. So the f of r theta is obviously just going to be this. To capture this whole shape, to capture all of the volume that we're talking about, how far does theta have to go?
2 pi.
0 to 2 pi. So here's my 9 minus r squared. Here's my r dude there. dr d theta. So theta's got to go from 0 to 2 pi. All the way around, that makes sense. And what's r doing as theta does that?
0 to 3. What is it?
Yeah.
Is it -3 to 3 or 0?
-3.
Oh, well.
So in this case, they're telling me that they actually just give it to me, don't they? R goes from 0 to 3. How we doing?
Why 0 to 3? -3 or 0 to 3?
This is where you have to remember that you can have negative r for polar, but you don't need it ever, as long as you give the correct angle. Since we decided to go from 0 to 2 pi, I don't ever have to kind of go back on myself, do I? At 0 degrees, this is all turned around. It's going to freak me out. So just forgive me for a second. Okay. So at 0 degrees, so that would be here, right? At 0 degrees, r goes from 0 to 3. Now you could say from -3 to 3, but then you have to be careful about what you do with your angle. And very often you have to be careful also about symmetry problems. You could lose some part of your answer, right? So you can either like overlap yourself and get more than you need, or you can lose part of your answer. So I do want to have that r go from 0 to something and capture the whole thing by making sure my theta goes up the whole way it should. So if I go all the way around 0 to 2 pi, I never have to go any more than 0 to 3. 0 to 3. How we doing? Remember your limits always come from what are you doing in the input plane. Don't worry about this, that's the height. That's caught by this function here, right? All I'm caring about is what's happening in this plane. It's just a circle with radius 3, so the radius goes from 0 to 3. To capture the whole circle, 0 to 2 pi. So multiply each part of that by the correct height, which is this. Add them all up, that should be the total volume under that thing. Yes, sir?
Since it's symmetrical, could you change the limits of the equation?
You could be a little smart about it. Well, what could you do?
Like I was thinking maybe from 0 to pi. And take out
Multiply by 2.
So if you do 0 to pi, and actually if you want to do 0 to pi over 2, what would happen?
Multiply by 4.
All right, let's try it. So let's try it this way first. So here I need r to go from 0 to 3. But I mean, let me ask, does that really?
Not really.
Not really. Right? In fact, if you want to get really technical, it adds a number that you don't really need there. Right? That kind of symmetry argument doesn't always lead to an easier problem to do, right? So it all depends on if it's going to be easy or not. You should come out with the same answer, yeah.
But sometimes we have to use it, right? If we get like 0 because we start at a point and then come back to that point.
So we saw an example of that earlier this semester where if you do go the whole way around, you actually cancel out part of your volume. Yeah. In this case, the heights are all positive all the way around. I don't think we're going to have the trouble here. Let's see what we get. This shouldn't be too bad here. Multiply that out. So then when you integrate the inside, what do you get? What are you integrating with respect to first?
R minus R squared.
dr, right? So then you get 9r squared 2 minus 4 evaluated from r equals 0 to 3. So r equals 0 is nice. When r is 3, I get 81 over 2. Let's see, 81 over 2 minus, where do we go? 81 over 4. So I get 81 over 4. Right. Half of 81 minus a quarter of 81 is a quarter of 81. And now, very often the last step is really easy. The integration with respect to theta. There's normally not going to be, no, let me be careful. A lot of your problems are going to have theta dependence, but some of them obviously will. So and without theta dependence, it's just tacking it on there. So we get 81 pi over 2. Oh, is that right? Okay. You can kind of estimate this. If you squashed it down a little bit, you could almost imagine you could make a cylinder. You'd have to kind of guesstimate how far you have to squash it down till it happened, but you can at least see if that makes sense. Okay. This section is not going to be really difficult. Let's try one maybe that's got a little bit more going on. Ooh, here's where they get gross.
Why here?
So example 3, page 900. Just saying page 900 makes me tired.
Yeah.
Good Lord. It's obviously not all in one semester.
5 more weeks.
It says, write an iterated interval for blah, blah, blah for the following region, blah, blah, blah. So the region outside the circle r equals 2. Blah, blah, blah. And inside the circle, where'd it go? R equals 4 cosine theta. And they're being really, really, really nice, like crazy nice. They're telling you here it's centered at 0, 2, 2, 0 with radius 2, yeah. So whenever you want to do these, find the in between two given areas, what do you think you need to do? So if I draw this, you can see the drawing in there, but it's this circle versus this circle here. So the area outside this first circle, but inside the second circle. So it's going to be this. That's the area that I want to use. So what do you have to find first?
Area of the second circle.
Now you gotta be careful, you can't, if you find the areas of both circles and do some subtraction, that's not gonna be right, because there's more, you know, they have the same areas, it's gonna come out to be 0. So the real key, who sees what really leads, yeah, the intersections. What is this? What is this? Yep. So all they give me to go on is, I'm going to set this here up. And all I want is the limits. What are the limits going to be? So here, let me start us off. Can you imagine, instead of being from 0, what's the radius going to start at now? What's the smallest the radius could be? 2. Yeah, this is the radius here. 2. So the radius is going to go from 2 to 4. Possibly. All right, gotta be careful. Why is it not necessarily, now as I'm drawing here, I kind of misled you a little bit. It is going to go from 2 to 4 here, but what's it doing from here to here? Or from here to here? So as theta goes from what to what? So maybe let's start there. How do I get what my theta is doing? I think this is what we were talking about earlier. I have to find those points there, don't I? Mm-hmm. What's that theta? What's that theta? So to find these two, of course, I just
2 equals 4.
yep, set them equal to each other.
Cosine theta equals 60.
So it's going to be where the cosine is smaller, cosine likes x, it's got to be far away from the x-axis, so 60. I like that. Pi over 3. So it could be, what do you think that is? It's a pi over 3, yeah. What do you think is wrong with saying, well, that's really 5 pi over 3. So why can't I say from 5 pi over 3 to pi over 3? Because that would actually be the negative integral of pi over 3 to 5 pi over 3, and that would capture all this area out there. In this case, actually, it would be the same. But your radius would be doing the wrong thing at the time. So you've got to be really careful about your angle that you make it. If it's back here, you make it negative. If it's out there, you make it positive. Unless you really do want to rotate a few times or something. Okay. So what's this thing going to look like? Oh, they didn't really tell us this today. This is just setting up the limits. So for my theta, it goes from negative pi over 3 to pi over 3. Now, why does my radius not just go from 2 to 4? Because now it's going from 2 to this circle. And that circle is 4 cosine theta. And that's probably the first thing you could realize, that r's got to be between this circle and that circle. So you see that showing up your limits. It's got to start at this circle and go to that circle. So for theta equal to 0, you do still get 2 to 4, don't you? Mm-hmm. But of course it's going to be more as you travel along here possibly, or I'm drawing it from the wrong place here. Why am I doing that? So there, there, there. Okay, make sure we're all talking about it. Because r's got to, of course, start at the origin, right? But I don't want to include all of this, do I? I want to include from here to there. That's what I want to use. Okay, cool. So from r equals to 2 to r equals to 4 cosine theta. That's what I want to use. So the same steps apply. You still sketch a graph of the region that they give me to work with. Right? Still sketch a graph. Sometimes you're going to find these, these intersections, so you can figure out one set of points. And this should feel very familiar. We've done a lot of these kinds of things where I say, here's r of 2, but I want to go from here to, so it's from 2 to whatever the hell this is. And that's 4 cosine theta. So that's why it's 2 to 4 cosine theta. Now, they didn't give me a function here, did they? Oh, okay, well, no. But if I wanted to find the area of that region using what I just set up, what do you think you would put in there? 1. Same thing as before. If I make this 1, I get a volume who's numerically equivalent to the area, because it's just times the thickness of 1. We talked about that before. Cool. Okay, that's probably the freakiest one you would see. They don't get too much freak here. Okay. So any questions about that? I mean, it might have seemed like polar coordinates. I mean, there are more complicated problems we could do than you're seeing here. But the basic idea is pretty straightforward. And those of you who skipped a step of just doing this quick sketch of the region, you're killing yourself. I need that visual. I do anyway. I don't know, some of you guys might not need it. But the visual confirmation of what the hell's going on. Okay. So any other questions? I mean, the only big thing they leave out is they actually talk about areas of regions like we just did. So they don't get much more complicated than this one.
We can only expect to see one of these problems on the test.
Yeah, yeah.
Sometimes it's easier to do the integration of color instead of the.
Oh, hell yeah. That's the whole point.
Yeah.
I'm glad you said that, because the whole reason we even look at this possibility of doing polar is because if my function has symmetry, you know, it's got circles involved, then obviously I should think about using cylindrical coordinates, which is what we're really doing, or at least polar inputs, right? It simplifies my function because my inputs are now defined by a single variable, not 2. Yeah?
Would you ever do this if you didn't have that case going?
You can imagine that you could. I mean, you can imagine that problems we've done would be easier to do this way. And you can imagine that problems like this for polar are not always this easy. I mean, I can give you a polar function that would actually be easier to look at in rectangular coordinates, of course. It works both ways. We don't really get that deep into polar coordinate volumes here. They just want to show you the main thing that we want to get out of this is that dA in general. dA can definitely be different. And it can get very different, such as when you get into something called spherical coordinate system. It can get remarkably different. I can't wait to try to do my pictures up on the board so that you understand the elements we're working with, the dV element in spherical coordinate system, and identifying what each side is so we can multiply together to figure out what the hell dV is. Same kind of thing we just did with the polar rectangles. So that is in our near future, right? Spherical coordinate systems is coming. So there's how many coordinate systems are there? What did you say? Infinite number. I like it. I think I might have said that earlier, or you just might know. You can make coordinate systems. There's families of coordinate systems, but you can make a coordinate system that works just for you, just for a problem you got. You can design a coordinate system. And if you wanted to do integrals, you'd have to figure out what the hell would dA be in your coordinate system. You have to do the whole process like we just did. Okay.
Dodecahedral coordinate system.
Say again?
Dodecahedral coordinate system.
All right, I like it. You should just try, trust me. If you haven't really seen too many coordinate systems, you should just try to Google coordinate system, go to Wolfram Alpha or do some kind of coordinate systems. It's really, Wikipedia should have quite a few. All right, so let's finish this up. 13.4. No. So with triple integrals, let's see what's a good first example. Oh, here's perfect. Example 2 in section 13.4. Is that it? No. Is that it? I think that's it. Yeah. Okay. So find the volume of the prism V in the first octant. So when I go to triple integrals, and they make a big deal out of this, but there's no reason to make a big deal on its own. How many ways could I write that? 6. So anyway, 3 times 2 times 1. So there's 6 ways to write that. dz, dx, dy, that. And of course, it all depends on what makes the problem easiest. Very often what you'll see is the last guy out here is where you decide the roof is. Because these two in here, this whole thing in the inside, would be going over your floor. So as x goes here and y goes there, then your z's are the roof overhead. You with me? And the roof could go from 0 to something or from 0 to something else as you move around. In this case, this might not be, well, this is not a bad example to start with. The roof in this case is nice because it's flat, right? It doesn't change. So it's not going to be a very interesting roof. Okay, cool. So what do we see here? We see that z goes from 0 to 6 effectively, right? Where am I at here? Oh, y, they kind of give it to me. X goes from what to what?
0 to 2.
So if we just draw the xy plane, and I just draw my the region of integration. If y equals 4 minus 2x, of course it starts at 4, and it goes down to 2. So you got my nice little triangle, so you can still draw this, your domain that you're integrating over. It's just that one thing triple integrals does for me is it allows for more interesting shapes than just a flat roof or something. It allows for, obviously, it allows for somehow integrating 4-dimensional objects. So one example of that, let me do a couple of general things real quick. And excuse me if I'm like a little scattered, I just didn't bring my notes for this section with me. Some general points to consider. If I had a box, let me just draw it without a freaking system there. It's a little easier. Right, so I can kind of put it here. Why not? And I actually want to know the weight of that box. I could have a density function that would relate to, like at this point.
Mass with the volume.
Yeah, variable density within the
Yeah, I was
I
just
like
gonna
it.
say it's uneven.
Yeah, it's a non-uniform mass distribution if you want to get into it, right? So the mass is distributed non-uniformly. So maybe the density increases as I go up or decreases as I go whatever. You with me? So I want to integrate over the volume that density function. And of course, I don't know if you guys, how many of you guys have taken physics, but density is defined to be mass per volume. With me? Mm-hmm. So then how do I get mass out of that? Multiply volume times density. And of course, those of you who have taken physics, you normally think of density as rho. Or you can think of charge density. It works the same way. So you can have a problem all about charge. You have a bunch of charges lining up on a rod, but they're not uniformly distributed. That kind of problem. Yeah, some of you guys are actually doing that probably right now. But that's what this captures, doesn't it? Mm-hmm. It multiplies density times volume. Density times volume is mass. I love it. So that's a really good example of not just the lame example. Here's the lame example for three integrals. Put a 1 in there. In fact, there's a problem we did last time. Go with me here. Don't worry. We'll get back to this. Let me see if we can find it real quick. Because I was talking to a couple of you guys. Yeah, there was. Oh, this is not the best example. Shit. What do I want? Too bad for me. There's example 3. Back in section 13.2. And it was this picture with this. So we could do this really quickly. That'd be interesting if we could. Not too bad. So it was the volume underneath that triangle. Remember that? And we had just 2 integrals because inside I put the z equals whatever this is. Now and in this case it was c minus ax minus by. And then was dy dx. Right, so that I think is one of the last ones we did. But I could instead, I could actually take one more integral and say z goes from 0. At any point, z goes from 0 to that roof. So it goes from 0 to this. And of course, I have a 1 in there. You with me? Sort of? Kind of? Okay. So, and actually I think earlier I was saying this backwards, but that's too bad for me. And the first step would really just reduce to this, wouldn't it? Because the integral of 1 would be z. You plug that in, you get that, minus 0, you get back to there. That, you can see why I call that the lame example of a use for triple integrals. It adds a step we really didn't need. So that's why I don't start there. It's a bad example. But there's a good example of why we need triple integrals. If it actually does depend on the volume, and it is different at every 3-part point. It's different. I need all 3 of them in here. And then I've got the function describing my density in this case at each of those physical locations. Okay. So enough of that. Whew. So back to this one. Where was it? Here it is.
Doesn't Z usually go on the inside?
Yeah, yeah. So that's what I was trying. Let's see if I can get this right. That's why this is not really the best example to start with. So in this case, they're looking at these 2 as being the inputs, so that YZ plane for some reason. And they're letting, let's see.
X be an output.
Where's this go? There it is. Okay. And they actually have dy dx. You see. So actually, I'll tell you what. Let's do this. This might be more interesting because I agree with you. Let's make z what it's supposed to be. Let's attack this problem like I was starting to earlier and see if we get the same answer they did. Which, how important is it that we consider xy to be the base? Not. I could consider yz to be the base, couldn't I? And then the roof would be this piece here. The roof would be the part over that. I just kind of turn this whole thing around. With simple shapes, and I call this a simple shape because it's a repeated shape. It's a prism. It's a simple shape. It's really easy to change the limits. It's almost like a rectangular region, but you got to be careful about this function if you change anything, right? So let's try to set this up in a different way. Let's not set it up the way they did. Let's see if we get the same answer. This could be interesting. I'm hoping. So let's do like we were starting to do here. So I want to set it up like this. Actually, I want to set it up like this. dz dy dx. And I was thinking that, but using the thing I'd written down earlier. So let me really try to make this quick. This would be my domain, my input, my floor. And this would be my roof. And that kind of mimics what I said here. This was like my roof. We didn't really need its own integral because I was just going to integrate that z over that region, but I could throw it into its own integral here if I really wanted to. So here, let's try to set this one up. Let's start from the outside. And what do you think you'll never have on this outside integral? What should you never have on the outside? What should it always be? constants. You with me? It's gotta be. Everything's well defined here. There shouldn't be, the answer should not be some function. The answer should be a number. There's a true volume here, right?
Mm-hmm.
So how in the world could your last integral itself have functions in it? Then your answer would end up being a function. That doesn't make any damn sense. You with me? I want to make a big point of that because I didn't make a big point of that last semester and I saw the results. So I'm going to make a big point of it this time. So start with x. What is x going to go from to?
0 to 2.
So x is going from 0 to 2. What is y doing as x does that?
0 to 4 minus 2x.
Yeah, so y is going from 0, oops. Yep, 0 to 4 minus 2x. I guess so for any x, y is going to go from 0 to that line. I like it. And what is z doing as everything else is happening?
0 to 6.
It's just going 0 to 6. It's a nice flat top. Z doesn't give a crap what x and y are doing. It's always freaking 0 to 6. And inside I've got, I think in this case we're just doing the volume, so there's just going to be a 1 inside. How we doing? Maybe, okay. So when you integrate this, let's see, 0 to 2, 0 to 4 minus 2x.
6. Okay.
Yeah, you'll get
6.
6, yeah, because you'll get z from your 6. Is that cool? Because of course you get z in there when you integrate that. Plug a 6 in, you get 6. 0.
6 times 4 minus 2x.
Yep, so you get here you get 6y, and y is going from 0 to 4 minus 2x. So you get 6 times 4 minus 2 is 24 minus 12x. And then finally this.
24x minus 6x squared.
Yep, minus 6x squared from 0 to 2. So it looks like you have 48 minus 24. Well, they didn't do it before. Oh, there it is. Now again, notice what they did. Their integral, they actually just turned these around. Because again, does z care what x and y are doing? In this case, no. All that matters is that x and y have to depend on each other. So the hardest part, the hardest way I could ask you to rewrite this is if I ask you to rewrite it like this. And that's not even that hard, is it?
No.
What did I do there? I changed the order of the x and the y. So the y has to be the one that's going from constant to constant. So you still use the same picture, except now that
You still correct.
y goes from 0 to 4, x is going from,
1 half y.
yeah,
Negative 1 half y.
so it's 2 minus 1 half y.
Plus 4.
Yep. You guys see that? That's where it would be, you'd have to be careful. Now, if z depends on x or y, then any changing of the limits would require you to be careful about your functions, your limits of integration.
Give us one like this.
Okay. So I'll tell you what. This is good because it actually gives me more time to do this. I didn't have any time, I didn't leave myself any time to create like a little worksheet that just focused on limits. Because normally the hardest part about these is figuring out what the limits are going to be. You with me on that? Once it's set up, the integration is normally pretty easy because they haven't thrown any trig substitution, any of that crap at us yet, right? And they're probably not going to throw. The worst I do to you is a u sub, probably. Maybe I shouldn't hold myself to that.
Sometimes we're going to have to convert to polar coordinates.
Yes, definitely. So next time I'll have an actual worksheet that we'll work on, just targeting limit problems to see if we can all do the limits correctly.